Hello again, this is where we left off in my last video, the Newton's Law of Cooling intro video. So in this video, we are going to continue from here. We're going to solve this differential equation for Newton's Law of Cooling, and after that, we will be looking at one example together. I think it's a good idea to watch that video first if you haven't done so already, since that video explains this law and this differential equation. Alright, now let's solve this differential equation. Separation of variables here. We're going to divide the t minus ts to the left side. We're going to multiply the d little t over to the right side. So d capital T over t minus ts is equal to k times d lowercase t. You can divide the k over to the left side too. Either way is correct, but to me it's just simpler to keep the k on the right side. Now we integrate both sides. Left side we're integrating with respect to capital T, and the t sub s is a constant, so we get natural log absolute value of t minus t sub s, plus the constant of integration there. On the right side, the integral of constant k with respect to little t is equal to k times little t plus another constant. Here we don't need to keep both constants here because we can easily combine them, so let's just call them c sub 1 on the right side. Now rewrite this log equation as an exponential equation, so the absolute value of t minus t sub s is equal to e to the kt plus c sub 1. Using properties of exponents, this is actually equal to e to the kt times e to the c sub 1. Notice that e is a constant, c sub 1 is a constant, so that the e to the c sub 1 is also a constant. So to keep everything simple, you can just rename e to the c sub 1 as a constant. Why don't we just call this constant c sub 2? So c sub 2 times e to the kt. By the way, the step that I just did there using the law of exponents to rewrite is necessary on the AP Calculus exams. So you have to rewrite e to the kt plus c1 as a constant times e to the kt. Usually when you're solving problems, you would know whether t is greater than or less than t sub s. So in that case, you would know exactly how to get rid of the absolute value. But because we're working on a general formula, we gotta consider two different cases. Case 1, when the temperature of the object initially is greater than the temperature of the surroundings. So without the absolute value, t minus t sub s is just equal to c sub 2 times e to the kt. Solving for capital T gives us t equals t sub s plus c sub 2 e to the kt. Case 2, when t is less than t sub s. In this case, removing the absolute value will give us t minus t sub s equals negative c sub 2 e to the kt. Solving for t gives us t equals t sub s minus c sub 2 e to the kt. I did not consider the case where capital T is equal to t sub s because in that case the temperature of the object will not be changing. And c sub 2 will just be 0 and the solution will just be t equals t sub s, which is a horizontal line. Now if you compare these two formulas for t, well again, plus c sub 2 minus c sub 2, they're both constants. So instead of writing two equations separately, you really can just write one equation. T equals t sub s plus c, where c is some constant, and then times e to the kt. One really typical example here. You might want to pause the video to read it first. Our goal is to find an equation for the temperature of the bread at any time. Which means in your final answer, you should only have two variables, capital T and lowercase t. So if you look at the equation on the top there, that means you have to find T sub s, C, and K. Our initial temperature of the bread is 350 degrees Fahrenheit, so T of 0, capital T of 0 is equal to 350 degrees. The room temperature is 70 degrees Fahrenheit, so that's telling us that T sub s is 70 degrees. After 20 minutes, the temperature of the bread has become 250, so T of 20 is equal to 250. On a test or quiz, I am never a fan of memorization, so you can set up your differential equation and go with the longer route instead of using the formula we just derived. As long as you know that the rate of change of the temperature is proportional to the difference between the temperature of the object and the temperature of the surroundings. And here, because we know that T sub s is 70, you can just plug that in. Also remember, we considered two different cases here when we tried to derive the general solution, but in this bread example, you already know that the initial temperature of the bread is higher than the temperature of the surroundings. So there's no need to consider the case 2 in the bread example. Anyways, I am not going to solve this differential equation again this time because we just derived the general equation on the top right there. So we can just use that equation this time. By plugging in the initial condition to the equation on the top, we get 350 equals T sub s, that's 70, plus C times e to the k times 0. So that's just e to the 0. E to the power of 0 is just 1. So we have C times 1, which is just a C, so C is equal to 350 minus 70, which is 280. Now plug in this second condition here into the same equation that was on top there a moment ago. So we have 250 equals 70 plus C, so we just found that C is 280, so plus 280 times e to the kt, and t in this case is 20. And let's just rewrite the exponent as 20k instead of k20. Now we do algebra to solve for k. Subtract both sides by 70, we have 180 is equal to 280 times e to the 20k. Divide both sides by 280. The left side is 18 over 28, which is 9 over 14. The right side just becomes e to the 20k. Now rewrite our exponential equation in the log form. So we have 20k, the exponent, equals log base e of 9 over 14. That sounds like natural log 9 over 14. 20k is equal to natural log 9 over 14, so k is equal to natural log of 9 over 14 divided by 20. The problem was asking us to find an equation for the temperature capital T of the bread as a function of time. So now we have it. Capital T equals T sub s, which is 70, plus C, which is 280, times e to the kt, where k is just natural log of 9 over 14 all over 20. We are pretty much done here, but there are ways to make your final answer look prettier. For problems like this, it's very likely that you can use your calculator. So instead of using a natural log 9 over 14 over 20, you can just plug that in your calculator. And your calculator should give you approximately negative 0.02209. Remember we said in the previous video that k should be a negative constant. And notice that our k here indeed is a negative number, which makes sense. So which means our equation for t would be approximately 70 plus 280 times e to the negative 0.02209t. Very quickly, if you are not using your calculator, but if you still want to make your equation look prettier, You can do 70 plus 280 times e, and then the exponent of e can be rewritten as natural log 9 over 14 times t divided by 20. If you pay attention to the parts that I circled in light green, e and natural log are inverse functions, so they will undo each other, which will leave us 70 plus 280 times 9 over 14 to the exponent of t over 20. Although I prefer the equations shown in dark green or in purple just because base e is a much more common base compared to 9 over 14. That was all. I hope those videos explained Newton's law of cooling well. See you soon. Bye bye.